Alright, hello everybody. So today we're talking about power series. So I'll say here, infinite series can be sums of more than just numbers. Right, so consider that here we're going to have the sum from n equals, this time 0 to infinity, of x to the power of n. Right, so let's just look at what this looks like. So if we plug in n equals 0, we're going to get 1. If we plug in n equals 1, we get x squared, x cubed, and so on. We're just going to get powers of x until we get, let's say over here, we get x to the n plus 1, and it's just going to keep going, right? It's an infinite series, so we're just adding together powers of x infinitely. So I'll say here, this is a geometric series, and I'd encourage you to pause here, think about what a and r should be. So what are you multiplying by to get, well, a is the first term, and what are you multiplying each term by to get to the next term? So here we're going to have a equals the first term, which is 1, and we're going to have that r equals, well, whatever you're multiplying to get each successive term. So r is going to be x, because you have to multiply this term by x to get to the next term. Okay, so we'll say here that the sum from n equals 0 to infinity of x to the power of n converges. Right, this is a geometric series, so it converges when the absolute value of r, which is the same thing as the absolute value of, we said r was x, so the absolute value of x is less than 1. Right, this is what we know about geometric series. I.e., so if the absolute value of x is less than 1, that means negative 1 is less than x is less than 1. And diverges when the absolute value of x is greater than or equal to 1, because that would mean that the absolute value of r is greater than or equal to 1, and it's a geometric series. Okay, so we've actually figured out when this series is going to converge and diverge, and it depends on x. So I'll say here, we can also look at a series like, so here this series is going to be the sum from n equals 1 to infinity of 2n minus 1 times x to the power of n. So let's just write out what the terms of this one are going to look like. So if you plug in n equals 1, you're going to get x. N equals 2, you're going to get 3x squared. For n equals 3, you're going to get 5x cubed, then 7x to the 4th, and so on. So you can kind of see the pattern there. You're getting the odd coefficients of each power of x. And here, we're just going to call these numbers coefficients. Okay, so let's write down the definition here. So definition, it's going to say a power series is a series of the form, and we're going to have the sum from n equals 0 to infinity of Cn, which is a function of n, so this is the coefficients as a function of n times x to the n, right? So up here Cn was this 2n minus 1. Okay. Which is, if you write this out, you're going to have C0 plus C1x plus C2 x squared plus C3 x cubed, and so on. Right, and sometimes this subscript, or sorry, this first term, sometimes this is n equals 0, sometimes it's n equals 1. It doesn't matter, either way, we're still going to call it a power series. And here I'll say where x is a variable and the CNs are coefficients. Okay. All right, so what we can say here is, as we saw here, whether or not a power series converges or diverges will depend on our choice of x. Right, because here we saw that if x is between these numbers, then it's converge, and if the absolute value of x is greater than 1, then it's going to diverge, or greater than or equal to 1. Okay, and the second thing I'll say here is that we can think of these as infinite polynomials. Okay, right, because this is just a polynomial with coefficients and x terms. It's just that it goes on infinitely instead of our standard polynomials. Okay, and I'll say here more generally, a series of the form the sum from n equals 0 to infinity of Cn times x minus a to the power of n is called a power series centered at a or about a. Right, so if we've got this form where we've got this x minus a inside of the exponent, we just say that it's centered at a. And you can ask the question here, and I'll just write it here on this other board, what happens when x equals a in this formula here? So we can ask here, what happens when x is equal to a? Then you can see what happens if you plug in a, then this is going to become 0. So what's going to happen is a power series centered at a always converges when x equals a. So that's going to be an important factor. And the last thing I'll say here is that we we usually use the ratio or root test for power series. Right, so all the examples that I'm going to do today are actually just using the ratio test, but sometimes you also want to use the root test. So both of those two tools are going to be the main things that we're working with in this section. Okay, so let's talk about an example. Okay, so example number 1 is going to say for what values of x. So s is in a parentheses because we don't know if there's multiple values, but for what values of x does the series from n equals 1 to infinity x minus 3 to the power of n over n converge? Right, so we said if we're using the root test, we want the whole thing usually to be to the power of n, but here only the numerator is to the power of n, so that's our clue that we're probably actually going to want to use the ratio test. Okay, so for the ratio test, it's right here for the ratio test, we're going to say that always we want to find the limit as n goes to infinity of the absolute value of an plus 1 over an. That's always what we're trying to find for the ratio test. Okay, so if we calculate this, this is the limit as n goes to infinity of the absolute value of, so here we plug in n plus 1 to get a sub n plus 1. So if we do that, we get x minus 3 to the power of n plus 1 over n plus 1. And now we're dividing by an. Remember, this is an. But if we're dividing by a fraction, that's the same thing as multiplying by the reciprocal. So I'm just going to take this and multiply by the reciprocal, which is n over x minus 3 to the power of n. Right? Because dividing by this fraction here would be the same thing as just multiplying by the reciprocal of it, which is right here. Okay. So now we've actually got to find this limit. And the key here is to always look for things that are going to cancel out. So this is x minus 3 multiplied by itself n plus 1 times. And this is x minus 3 multiplied by itself n times. So we're certainly going to get a lot of copies of x minus 3 canceling out with each other. So that's what we're going to try to do here. So I'll say that this x minus 3 to the n is going to cancel out with this x minus 3 to the n, and that plus 1 just means that we're going to be left over with x minus 3. So we're going to get the limit as n goes to infinity of the absolute value of, so n of the copies of x minus 3 are going to cancel out on both sides, so you're going to be left with x minus 3 times n over n plus 1. Okay. And now you'd say, well, the way we solve this type of limit with n, so this doesn't depend on n, so you can kind of treat this like a constant. But we're trying to take the limit of this part, and notice whenever we're trying to take the limit of this fraction, we divide both sides by the highest power of n in the denominator. And if we do that, we're going to get 1 over 1 plus 1 over n. This 1 over n is going to go away, so we're just going to get 1. Okay, so I'd encourage you to work through that. But here we get the limit as n goes to infinity. Well, if you take the limit, if you take the limit, you're just going to get the absolute value of x minus 3, because this part is going to go to 1. And we're going to say here that this, using the ratio test, this is definitely going to converge, or let's call this L, sorry. So what we can say is, so the series converges when L, which is equal to the absolute value of x minus 3, is less than 1, because that's what the ratio test said. Whenever this limit thing is less than 1, we know that our series is going to converge. Okay. And if we go ahead and say that this absolute value is less than 1, then that means that negative 1 is less than x minus 3 is less than positive 1. So that's how you just get rid of those absolute value symbols. You just wedge it in between those two. And if you just add 3 to both sides, then you're going to get that 2 is less than x is less than 4. So it's going to converge when x is between 2 and 4. And we can say similarly, and diverges when absolute value of x minus 3, which was equal to L, is greater than 1. So we can say, i.e., when x is going to be outside of this range, so less than 2, or x is greater than 4. But notice I didn't say anything about when x is equal to 2 or when x is equal to 4, because that would be when L is equal to 1. And remember, the ratio test doesn't say anything about when L equals 1. So I'll write that down on the next page here. Recall that the ratio test is inconclusive when L equals 1. So solving for when L equals 1, we know absolute value of x minus 3 equals 1. That's going to mean that happens when x equals 2 or x equals 4. So those are the 2 points that we need to test. So I'll say here, we need to test these separately. Okay, so first we're going to test x equals 2. Okay, so now we just plug in x equals 2 into our series, and we're going to see if it converges or diverges. So we're going to have a sum from n equals 1 to infinity of 2 minus 3 to the power of n over n, which is the same thing as the sum from n equals 1 to infinity of negative 1 to the power of n over n. But notice here, this series we actually already had a name for. So we already called this the alternating harmonic series, and we know that this one converges. Right, so whenever x is equal to 2, we get a convergent series. And the next thing, the last thing rather, that we have to check is when x equals 4. So if we plug in x equals 4, we're going to get the sum from n equals 1 to infinity. If we take 4 minus 3, we're going to get 1 to the power of n over n, which is just 1 over n of 1 over n. But notice here that this is the harmonic series, and we already said that this one diverges. Okay, so we know that it's going to diverge when x equals 4, and it's going to converge when x is equal to 2. So we can say, so power series, just in conclusion, we've got the power series here. I'm just going to rewrite it. So we've got x minus 3 to the power of n over n converges for all x in the interval from 2 to 4, not including 4, but including 2, so we put a brackets around 2 and a parentheses around 4, i.e. for 2 is less than or equal to x is less than 4. Okay, so whenever x is in this range, our series is going to converge, and whenever x is outside that range, we know that our series is going to diverge. Okay, so let's just do some more examples using this. Okay, so example number 2 is going to say for what values of x does the sum from n equals 0 to infinity of n factorial times x to the n factorial times x to the n converge. Okay, so again, we're going to use our favorite tool, the ratio test. It's our favorite tool for this section. So it's going to say that the limit as n goes to infinity of the absolute value. So here we just need to plug in an plus 1 over an. So if we do that, we're going to get the limit as n goes to infinity of the absolute value. If we plug in n plus 1, we're going to get n plus 1 factorial times x to the n plus 1. And if we plug in n, we're going to get n factorial times x to the n. And we just got to simplify this thing. So remember, n plus 1 factorial is multiplying all the numbers less than or equal to n plus 1, all the integers less than or equal to n plus 1. And this is multiplying all the integers less than or equal to n. So notice this is going to be, if we write this out, so this is going to be n plus 1 times n factorial. And on the bottom we had our n factorial. And here we're going to get x times x to the n. And on the bottom here we have x to the n, right? Because x to the n plus 1 is just x times x to the n. Okay. And notice what we can cancel here is these 2 copies of n factorial and these 2 copies of x to the n. So all of that is going to cancel out. And what we're left with is the limit as n goes to infinity of the absolute value of n plus 1 times x. Now, if n is going to infinity, what is this going towards? Well, here you've got an n, so it looks like this is going to infinity. But what's the only circumstance when this is not going to infinity? Well, what can x be equal to make this not infinity? The answer is going to be 0, right? Because if x is equal to 0, it doesn't matter what n is doing because this is just being multiplied by 0. So we'll say here that this is equal to infinity unless x equals 0. So the sum from n equals 0 to infinity of n factorial times x to the n diverges for all x not equal to 0 and converges only when x equals 0. Okay. So let's do one more example here. Example number 3 is going to say for what values of x does the sum from n equals 0 to infinity of x to the n over 2n factorial converge. Okay. So again, we're going to try to use the ratio test. So we're going to take the limit as n goes to infinity of the absolute value of an plus 1 over an. So here we plug in n plus 1, get x to the n plus 1 over, we're going to get 2 times n plus 1 factorial. And then here, now we multiply by the reciprocal of an, right? Because we've got an plus 1 over an, which is the same thing as multiplying an plus 1 by the reciprocal of an. So we're going to multiply this by 2n factorial over x to the n. Okay. So now we just got to multiply these things out, because this is going to be equal to the limit as n goes to infinity of the absolute value of, so we can go ahead and just, I'm going to just rearrange things, x to the n plus 1 over x to the n times 2n factorial over, this was 2n plus 2 factorial. Okay. And now again, we just do the same thing that we did over there. So we can rewrite this as the limit as n goes to infinity. But the absolute value of, we can write the numerator here is x times x to the n over x to the n. And for the second fraction, we can write this as 2n factorial over, now here the denominator is 2n plus 2 factorial. So this is going to be 2n plus 2 times 2n plus 1 times n factorial. Oh, sorry, oh, that's not what I meant, right? Times 2n factorial. Okay, so now you can see what cancels. This x to the n is going to cancel out, and this 2n factorial is going to cancel out. So now we're just left with, if we rewrite this, we're going to be left with the limit as n goes to infinity of the absolute value of, this will become x over 2n plus 2 times 2n plus 1. Okay, but here n is going towards infinity, so this denominator is getting infinitely big, meaning that the overall fraction is getting infinitely small. So this is going to be equal always to 0 no matter what x is going to be. Because this fraction, x isn't changing, but this denominator is getting infinitely big, so you're going to get closer and closer to 0. So we'll say here, so L equals 0 for all x, which is going to imply that L is less than 1 for all x. And remember what our conclusion was, if L is less than 1, then our series is convergent. So the sum, ooh, that's messed up. The sum from n equals 0 to infinity of x to the n over 2n factorial converges for all values of x. Okay. All right. So the next thing to note, let me erase the next board. Okay. So I'll say notice in all our examples, our power series all converged on single intervals single intervals like, so with one example, I think it was the first example, we had the interval from 2 to 4, rather than intervals like, right, so a different type of interval would be if we had, ooh, that's a bad bracket. If we had the interval from -2 to 5, parentheses, union, parentheses, 11 to 14, and now with a bracket. Right, so this is actually an interval with two different pieces, rather than what we got in example 1, which is just one piece on the interval. Okay, and I'll say here, this isn't a coincidence. Okay, so we're going to have a theorem. It's called Theorem 1. Well, I don't like the circle. Let me get rid of the circle. But Theorem 1 is going to say the power series so we're going to have the sum from n equals 0 to infinity of Cn times x minus a to the power of n has only 3 possibilities. Ooh. Okay, so the first possibility here is going to be that the series converges only when x equals a. Right, so I forget what the example was, but we actually found one of these examples of them. So one possibility is that it converges only when x equals a. So we've had, I forget which example it was, but one of them, it only converged when x was equal to 0. The second possibility, the series converges for all x. So that was this example. Every value of x, for every value of x, our series was actually convergent. And the last case, case number 3, is going to say there is a positive number r such that the series converges if absolute value of x minus a is less than r and diverges if absolute value of x minus a is greater than r. Right, so these are the only three possibilities. So either the series converges only at x equals a, or converges for all x, or whenever there's some number r such that for every x value in this range, the series is going to converge, and for every x value in this range, the series is going to diverge. But notice it didn't say anything about when x is equal to r. So that's like an example, I think it was example 1, where we had to test the endpoints to see what happens when x is actually equal to r. So you have to be a little bit careful there. But I'll say here in a definition, so definition, the number r in theorem 1 is called the radius of convergence of the power series So in case 3, we can figure out exactly what r is equal to, but what about cases 1 and 2? In case 1, we say r equals 0 because it only converges when x is equal to a, and we'll say in case 2, we say r equals infinity because it converges for all values of x. So we're going to say here that r is equal to infinity. Okay, and another definition. The interval of convergence of a power series is the interval of x values satisfying that the absolute value of x minus a is less than r. Right, so the interval of x values satisfying this condition, we'd say that that is the interval of convergence because that's the interval of x values where the series actually converges. And one last thing that I'll note, and this is very important, so I'll put 3 asterisks next to it. We'll say we always need to test our endpoints as we did in example 1. Okay, so we just have to be careful there to also test our endpoints. Okay, so next we're going to look at number 4. Example number 4. Okay. So for number 4, I'm going to say find the radius and interval of convergence of, so we're going to have the series from n equals 1 to infinity of -3 to the power of n times x to the power of n over square root of n plus 1. Okay, so again, for all these problems, we've been using the ratio test. We would be using the root test if we had the whole thing to the power of n, let's say, but here only these two parts are to the power of n, so we don't want to use the root test. So we're just going to use the ratio test. So for the ratio test, again, we need to compute the limit as n goes to infinity of the absolute value of an plus 1 over an. So an plus 1, if we plug in n plus 1, we're going to get this, x to the n plus 1 over square root of, if you plug in n plus 1 here, then n plus 1 becomes n plus 2. And now we multiply by the reciprocal of an, so we multiply by the square root of n plus 1 over -3 to the power of n times x to the power of n. Okay. So now we can certainly cancel a few things. But first, let's rearrange things. So I'll rewrite this as the limit as n goes to infinity of the absolute value of, let's compute, what's the word? Collect, that's the word I was looking for. Let's collect these things with the -3s in these terms with the x's. So if we do that, we're going to get -3 to the n plus 1 times x to the n plus 1 over -3 to the power of n times x to the power of n times our square root of n plus 1 over the square root of n plus 2. Okay. So now we can see that we're going to cancel a few things, because you can rewrite this. Let me just write out an additional step here to make it less confusing. Here, -3 to the power of n plus 1, we can factor out a copy of -3. So we've got -3 times -3 to the n. And similarly, here we can factor out an x. So we've got x times x to the n over -3 to the n times x to the n. And again, we're multiplying by the square root of n plus 1 over square root of n plus 2. Okay, so now we can see what cancels. We're going to cancel this -3 to the n, and we're going to cancel this x to the n. So now let's see what happens. We're just left with -3 times x. So we've got the limit as n goes to infinity, the absolute value of -3x times the square root of n plus 1 over the square root of n plus 2. And notice if n is going towards infinity, then the numerator, if n is going towards infinity, then the numerator is essentially the same thing as the denominator, because they just differ by this plus 1, right? But if this n is really big, then that doesn't really matter. This is going towards 1, right? This is approaching 1. If you wanted to, you could do the whole thing where you divide everything by n and whatnot, but you don't need to do all that. You can just say, well, this numerator is essentially the same as the denominator. As n is getting infinitely big, they're just going to go towards, they approach the same number. So they're going to both, when you divide one by the other, you're going to go towards 1. So let me just write that. This goes towards 1. Okay, so we're going to approach as n goes to infinity the absolute value of -3x, but it's the absolute value, so we don't need the negative sign. So we just got the absolute value of 3x which is 3 times the absolute value of x. And I'll say that this is convergent, so this is L, right? So this was our number L, and this is convergent when L is less than 1. So it's convergent when L, which is 3 times the absolute value of x, is less than 1, which also means, so if you divide both sides by 3, that means that absolute value of x is going to be less than 1/3, so that gives us our r. That's going to be our radius of convergence, because we're saying here that absolute value of x has to be less than 1/3. Okay. So if absolute value of x is greater than 1/3, then we know it's divergent, again by the ratio test. But if absolute value of x is equal to 1/3, we don't quite know what happens. So I'll say here the radius of convergence is 1/3. And to find the interval, we need to test the endpoints of the interval from -1/3 to 1/3. Okay, so that's the last thing we got to do. We just got to test those endpoints. So let's try the first endpoint of x equals 1/3. So we just plug that into this series. So if we do that, we're going to get the sum from n equals 0 to infinity of, so we plug in 1/3, so we're going to get -3 to the power of n times 1/3 to the power of n over square root of n plus 1. And notice here, this 1/3 times a third times 3 is going to cancel out, and you're just going to be left with that minus sign. So we're going to have left over here the sum from n equals 0 to infinity of -1 to the power of n over the square root of n plus 1. And notice here that this is an alternating series, so we're going to use the alternating series test. I'm not going to go through the details. I'd encourage you to go through the details, but I'll say here that this converges by the alternating series test. Okay, and the last thing we need to check is for x equals -1/3. So if we do that, if we plug that in, then we're going to get the sum from n equals 0 to infinity of -3 to the power of n times 1/3 to the power of n over the square root of n plus 1. And notice here, oh sorry, this was -1/3, right? So this is -3 to the power of n times -1/3 to the power of n. So everything in the numerator is going to cancel out. So you're going to get sum from n equals 0 to infinity of 1 over the square root of n plus 1. But notice here, if we use the direct comparison test, this series is very similar to 1 over square root of n. So I'm just going to say that this is actually going to be equal. So you'd have to check this. But this is going to be equal to sum from n equals 1. Oh, sorry, I messed up. Okay, sorry. I messed up the explanation there. But what I want to say here is, here you're starting at n equals 0. If you instead start at n equals 1 to infinity, then all you have to do is get rid of this plus 1. Right? So the way you check that these two are actually the same series is you just start plugging in the numbers. Right? So you plug in 0, then you plug in 1, then you plug in 2, then you plug in 3 for n, And you're actually going to get the same thing here if you plug in 1, then 2, then 3, and so on. Right? So reindexing this starting part right here is the same thing as corresponding to getting rid of that n plus 1. Right? So that's just a little bit technical, but it turns out that this is going to give you this. And this is the sum from n equals 1 to infinity of 1 over n to the 1/2. And remember, this is a p-series with p is less than 1, right? So it diverges by the p-test. Right, because p is less than 1, so we know that this thing diverges. So therefore, the interval of convergence is going to be, so remember, it converges when x is equal to 1/3, but not when x is equal to -1/3. So -1/3 with parentheses and 1/3 with brackets. So that's going to be our answer. This is our interval. Okay, so I just want to go over one last problem. Okay, so our last problem, number 5, is going to say find the radius and interval of convergence of sum from n equals 0 to infinity of n times x plus 2 to the power of n over 3 to the n plus 1. Okay. Right, so again, we want to try using the ratio test. Right, so I'd encourage you to try to work this out on your own. But here, if we use the ratio test, we're going to get the limit as n goes to infinity of the absolute value of, if we plug in n plus 1, times the reciprocal of an. So it's going to be 3 to the n plus 1 over n times x plus 2 to the power of n. So again, it's the same thing where we're just trying to collect terms and cancel things out. So we're going to get the limit as n goes to infinity of the absolute value of, this would be, let's say we've got 3 to the n plus 1 times x plus 2 to the n plus 1 over 3 to the n plus 2 times x plus 2 to the n. Okay. And this is times, this would be n plus 1 over n. Okay. And now we can see what we can cancel. Here, if you just factor out a 3 here, then you can cancel 3 to the n plus 1. So we're going to write this as the limit as n goes to infinity. The absolute value of, here, cancel out 3 to the n plus 1. You get a third. Let's just write that on its own. Here, if you cancel out x plus 2 to the n plus 1, you're just going to be left with 1, or sorry, that's not what I meant to write. X plus 2 over 1. And here, if you can't, or sorry, you can't cancel anything out here, so you're just left with the n plus 1 over n. Okay, so now we can say, well, if n is going towards infinity, again, we run into the situation where we have this fraction, and the numerator is going towards infinity just as quickly as the denominator, right? So you would do the thing where you divide both sides by n, and then this 1 over n is going to go towards 0, so you're going to eventually get 1, but here this is going to 1. So your answer here is going to be absolute value of x plus 2 over 3. That's going to be your L, but we can actually rewrite this as 1/3 times the absolute value of x plus 2. That is L. And we know if our series is going to be convergent, then L better be less than 1. Well, L equals 1, it could be convergent, but we know our interval of convergence. To determine that, we need to figure out when L is less than 1. So we're going to write here that absolute value of x plus 2 over 3 is less than 1. Now we multiply both sides by 3. So the absolute value of x plus 2 is less than 1/3, which means that x plus 2 is between negative 1/3 and 1/3. And if we just subtract 2 on both sides, then what we're going to get, oh, sorry, I divided both sides by 3 for some reason. It's not what I was meant to do. I need to multiply both sides by 3. So if we multiply both sides by 3, that's the value of x plus 2 less than 3. And then that means that negative 3 is less than x plus 2 is less than positive 3. And then we subtract 2 from both sides. So negative 5 is less than x is less than 1. So that's going to be our interval, is between negative 5 and 1, but we need to figure out the endpoints as well. So what this does tell us is, if you look at the length of this interval, it's going from negative 5 to 1. So the radius there is actually going to be 3, because the radius would be half of the length. But now we need to figure out the endpoints. So the radius of convergence is going to be this number, 3. And now we just need to figure out the endpoints. So we'll say here test endpoints of the interval from negative 5 to 3, or not 3, 1. So if we want to test these endpoints, then we'll say for x equals negative 5, if we just plug that in to our series here, then we're going to get the sum from n equals 0 to infinity of n times negative 5 plus 2 to the power of n over 3 to the n plus 1. So if we compute this, this is going to be the same thing as the sum from n equals 0 to infinity of n times negative 3 to the n over 3 to the n plus 1. And notice we can break this up as negative 1 to the n times 3 to the n. So if we do that, we're going to get, let me just write this over here. So we're going to get sum from n equals 0 to infinity of n times negative 1 to the n times 3 to the power of n over 3 to the n plus 1. And notice n copies of 3 are going to cancel out, because you've got n copies of 3 in the numerator and n plus 1 in the denominator. So you're going to get sum from n equals 0 to infinity of n times negative 1 to the n over 3. And notice what's happening here is you can go ahead and try using the test for divergence. Which, remember, was just a fancy name for saying take the limit as this thing goes towards infinity, and the limit as this goes to infinity doesn't exist because it's alternating. And this is getting infinitely big, right? So just because it's alternating doesn't mean it doesn't exist. So if this were 0, if it were multiplying by 0, that would be fine. But this part is getting infinitely big, and this part is alternating. So if you multiply those two together, well, that's certainly not non-zero. So we'll say that this diverges by the test for divergence. Okay, so again, I encourage you to check that. But now we just got one more case. So let me write this out. This is x equals 1. And if we plug in x equals 1, we're going to get the sum from n equals 0 to infinity of, here if we plug in 1, n times 1 plus 2 to the power of n over 3 to the n plus 1. So this is going to be 3 to the n over 3 to the n plus 1. That's the same thing as the sum from n equals 0 to infinity of, 1/3 times n. But if n is getting infinitely big, then adding all these numbers together, that's going to be infinite. So I'll say that this diverges, again, by the test for divergence. Because if you take the limit as this goes to infinity, as n goes to infinity, then this is going towards infinity, which is certainly not 0. So again, this is going to diverge. So our conclusion is, so the interval of convergence is the interval from -5 to 1, and not including the endpoints. So we're going to use parentheses there.